Welcome to this course on Instanton physics. Instantons are a creation of theoretical physicists dating back to the mid-1970s. They have found great utility not just in particle physics and cosmology, but also now in condensed matter, in chemical physics, and also, most mysteriously, in financial mathematics. Of that, I have no clue. This is going to be a rather long course. Well, it's a short course, but it's going to be quite intensive. And I would like to put before you the curriculum at the very outset and explain what we are going to be doing. So let's start. You see that we are going to first concentrate upon quantum mechanics. Quantum mechanics, I can't give you an exact level because there's no such thing as an exact level, but roughly at the level of a graduate course. We'll talk about the Feynman path integral, and I will today give you a derivation of the Feynman path integral, starting from quantum mechanics as you have learned in your undergraduate years. In the next lecture, we will go to the Feynman path integral in imaginary time, what is called the Euclidean action, and see why it is so much better and so much more convenient relative to ordinary time. Then we will apply it to simple situations, first to a free particle, then a harmonic oscillator, and then to the symmetric double well. Now, the whole purpose behind instantons is to give you a handle on tunneling, quantum tunneling. And this will actually be our main purpose. Using this, we will study how certain states, metastable states, decay, how long it takes them to decay, and this is the problem which is at the core, how to compute the decay rates. In this process, we'll have to meet with some rather interesting mathematics. So here it is, path integral, imaginary time, symmetric double well, decay of metastable states, and then the functional determinant. So we're going to have to deal with infinite determinants, and they're going to be a real pain. But we'll learn how to deal with them. The next part of the course will be related to quantum field theory. Quantum field theory is quantum mechanics, but with an infinite number of degrees of freedom. Now, in the first part, I'm going to talk about just a single degree of freedom, and it can't be simpler. You have a single particle moving in a potential, and that'll be it. But when we start talking about quantum field theory for in the simplest situation, which is a scalar field, we'll see how those very same ideas are useful and how they can be adapted. We will then look at the tunneling of quantum fields from one state or one phase to another phase. And this is going to introduce something very new and different. It's not going to be just your particle going over a potential barrier. It's going to be much more interesting. And I'll tell you why that is. That will then bring us to the concept of instantons in field theory. And the simplest instanton is called the O4 instanton. So it's a rotational symmetry in 4 dimensions. And we'll derive the formula for that. We'll do some things with that, not very much. And then we'll come to something more substantive. And this is now getting us into really hardcore theoretical physics, that is gauge theories, and the infinite number of different vacua that they have. So in quantum mechanics, you also have an infinite number of vacua, but this is going to be much more interesting. Then we'll talk about effective actions and finally apply that to the real problem, which started off this whole investigation. How will the universe end? Now, there are lots of different ways it can end, but this is the particular way that inspired the whole application of instantons to quantum field theory. Okay. This is a well-explored field. There are hundreds of papers that have been written since 1975, 76. But now there are textbooks. There's a very good textbook that you see over here, Theory and Applications of Instanton Calculations by Paranjape. And it's a rather recent book, 2022. And you can get it, you know where from. So this is the man who started it all, Sidney Coleman. And one of my greatest regrets is that I didn't take a course in quantum field theory from him. I could have. It was just down the road, Massachusetts Avenue. But anyway, this is the paper that launched it all, 1977. This is just as I was finishing my PhD. The abstract of this paper reads, "It is possible for a classical field theory to have two homogeneous, stable equilibrium states with different energy densities. In the quantum version of the theory, the state of higher energy density becomes unstable through barrier penetration. It is a false vacuum." And then he goes on to say that he's going to do a semi-classical analysis. What happens when you go from the false vacuum to the true vacuum? Listen to what he says. "Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some creatures capable of knowing joy. This possibility has now been eliminated." Very, very grim. But not to be taken too seriously. Okay, so now let's come to quantum mechanics. So for quantum mechanics for babies, you talk about, here is a particle that comes along with some energy. It doesn't have enough energy to go over, so it goes up, and then it rolls back down. But quantum mechanically, it can go through. It can tunnel through. And, well, that's all that you tell babies. But when you do undergraduate quantum mechanics, then you learn a little more, and you learn that if there's a particle, which is on this side, A, and it has a certain energy, and that energy is not enough to go over the barrier, yet it can tunnel through to the other side, get to position B, and all who have read undergraduate quantum mechanics have studied the WKB approximation. This is Wenzel Kramer's Brillouin, invented, I think, in the 1930s and applied to tunneling problems. It gives you the amplitude to go from A to B, and that's like this. Exponential of -2/h bar, integral A to B of this quantity, square root of the potential, V of x minus E. And where this becomes 0, there you have the classical turning points A and B. So at these points, V of A and V of B are both equal to E, and the square root vanishes. So in terms of potential arbitrary potential barrier. It's here. So here's V of x. Here's the particle which has got insufficient energy E to surmount the barrier. And it would be sent back, except for the fact that it can tunnel across, which means that its wave function is non-zero inside. So here it is a free particle. You see the oscillatory wave function, and here again it is oscillatory. Okay, now this is an explicit formula for the transition amplitude from A to B. You notice over here that H bar is in the denominator. If I send H bar towards 0, I make it smaller and smaller, this will be e to the minus 1 over infinity. E to the minus infinity, which means that this will vanish. Now, this is also telling you that this is fundamentally non-perturbative. No matter how high you go in perturbation theory, see, perturbation theory is always in a small parameter. So the 0th order is where you start. The first order is supposed to be better. Second, third, fourth orders are supposed to be better, 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 better. But even if you go to infinite order in perturbation theory, you cannot recover this result. How this is derived, I'll leave you to read from a book like maybe Griffiths, many other books. It's standard stuff. The problem with the WKB approximation is you can't improve it systematically. You see, the beauty about perturbation theory is that you can go systematically and improve your results, but you can't do that in a non-perturbative scheme. So the Feynman path integral that we're going to study is going to provide an alternative to WKB. Now, people have tried to improve WKB, but it becomes so complicated that it's not worth the trouble. You just get into so many complications, it's not worth the trouble. Okay, you know who this man is. Richard Feynman. He invented, I think this was probably his greatest contribution to physics, the Feynman path integral. And it's absolutely wonderful in terms of in terms of how it is a conceptual leap, how it takes you into an altogether different way of looking at quantum mechanics. Now, quantum mechanics is by itself pretty mysterious. He took it to another level of mystery. And now we're going to get slowly into that. Here's the double slit experiment that everyone studies who's taken a course in quantum mechanics. Okay, typically what you have is you have a source of electrons or a source of light or a source of protons, whatever, doesn't matter, everything. Waves and particles are the same thing. So from the source A to the screen B, there is a slit. There are two slits over here through which the electrons can go. They can go via this path, or they can go via this path. And now this path has got a certain amplitude associated with it. So has this path got an amplitude associated with that? The total amplitude is the sum of the two amplitudes. And now you know that if you square the amplitudes, you get the probability. Okay, now if you were to take the square of this, by square of this I mean this times its complex conjugate, then you'll get an interference term. That interference term says that at some points you're going to have a maximum, at some points you're going to have a minimum. So there'll be a maximum over here. As I go up, it'll go to a minimum, then to a maximum, then to a minimum, then to a maximum, and this will continue indefinitely, although of course the fringes will get weaker and weaker. Well, I can repeat this experiment and use 2 double slits. So here there are 4 paths. I've only shown 2, but there's this path as well, going from here to here, here to here, here to here. So that's path number 3. Here's path number 4, here to here, here to here, here to here. So we have a total of 4 paths, and now the rules of quantum mechanics say that you multiply it by its complex conjugate, and that gives you the probability of going from A to B. In other words, to get the amplitude, you have to sum over all the paths over here, which are 4 in number. And now this is leading us to the idea of the path integral. That is, what is a summation? It's a large summation then becomes an integration. We know that from calculus. Okay, let me develop this a little more. So here is a particle at the point A, xa, at time ta. It has to reach this point xb at time tb. And now it's not 2 slits, it's 1, 2, 3, 4, 5 slits. I could make it 50 slits, or 5 million slits, or 5 billion slits. But even more, I can put not 1 slit, but 2 slits and 2 billion slits. So you can see that an electron which starts out at this point can go to this point by how many ways? A lot of ways. Okay, and this is now bringing us to the idea of the Feynman path integral, that the amplitude to go from A at a certain time to point B at another time is you sum over this path, this path, this path, you sum over all possible paths. And now, the question is, which paths are allowed? Okay, it could be that an electron, in going from one atom to a neighboring atom, it will first go to the moon and come back. Sure, it can do that. All paths are allowed, that path is allowed. And we're not going to stop the electron from doing that. It's allowed to do that. It can go whichever way it wants. So that's okay, as long as the path is smooth. But what if the path is jagged? So it goes back, forth, back, forth. What if it is fractal? Everyone here has heard of fractals, right? If you measure the coastline, so you're at one point on the coast. Let me draw this. Jagged coastline, there's a sea over here, this is land, and you're walking along. If you are a sufficiently small creature, you will see lots of obstructions and you will move back and forth and back and forth. If you are a point particle, then you can move on a path which is non-differentiable. In fact, it can be fractal. So in fact, in traveling from here to here, you will have to travel an infinite distance. Are we allowed that kind of path over here? Yeah, but it won't make a difference because it'll have a huge S associated with it, action associated with it. I'm going to tell you what action is, but for now, we say pretty much most paths, but they have to be well behaved. And you see, now we're going to get into an area of mathematics called measure theory, and I am not going to do that at all. So the question now is how many paths? And the answer is, of course, infinite, but are they countably infinite? Or are they, like the real numbers, uncountably infinite? It turns out that paths that we are capable of addressing and which are the important paths, and the others won't matter at all, are the paths which are denumerable. Now, this is a question which is absolutely stunning. How can the particle travel simultaneously on all paths? So it's traveling on this one and this one and this one and the billions and zillions of particles of the paths that exist. Well, how can it travel on two paths? Well, my question to you is, how can a cat be dead and alive at the same time? Of course it can be. Yeah, that's the old Schrödinger cat puzzle. But we know it's not a puzzle. I mean, this is what quantum mechanics is. So it can simultaneously be traveling on every path, on all paths, on an infinite number of paths. It's quite mind-boggling, but okay, we've got to adjust our minds. We can't adjust quantum mechanics. Now, this is a question which is very interesting and for which I don't have an answer, which is, why do all paths have exactly the same weight? See, over here, e to the is, s for every path. S is different for every path, but there's no number in front over it. It doesn't say 2 times this and plus 3 times e to the is 3 over h bar. Actually, you'll get the answer for this question from quantum mechanics. I won't give you because I don't understand quantum mechanics, but quantum mechanics will give you the answer. We'll see it very shortly, why all the paths have the same weight. Why do we see only one single classical path? I mean, if you throw a stone, it goes from one side to the other side. It follows a parabola, and you never see it wiggling on the way. When you drop a stone, you see it falling straight down. You don't see it wiggle as it falls to the ground. The answer to this is actually quite easy. So it's that the paths which are close to the classical paths have similar phase, a very close phase to that of the classical path, whereas the ones which are further away, like this path over here or this one, they have phases which will interfere. And when they interfere, they destroy each other. Only the paths which are close to the classical path will interfere constructively, and the others will all cancel out amongst themselves. Now, this can be rigorously shown mathematically. We'll see how this can be understood in a different way as well. By the way, you've always heard, haven't you, and also seen in the lab, that the angle of reflection and the angle of incidence are the same for light. Have you ever thought about why that is? Because look, it could be that you have light coming from here, bouncing off from here reaching here, but equally it could be from here or an infinite number of different paths which all start from A and end at B. But it is the constructive interference of light which gives you a single path. And that's what light classically does. It has the angle of incidence and angle of reflection exactly the same. And this, by the way, I presume you've heard of Fermat's principle of least time. So there is a minimum principle over there which actually tells you that this path is the actual correct one. Okay. Now we have to get a little serious. And suppose I have a state at time 0, and I want to know what it is at a later time. Let's call that time t. Well, then I apply the operator over h bar. And this is what gives me the state at a later time. So this is the evolution operator, e to the minus h t over there. So the Hamiltonian is called the generator of time translations. This is actually nothing but the Schrodinger equation, because if I do this, I h bar d by dt psi of t, well, what do I get? So this comes down over here. So this becomes h bar. And then the same thing. And this is just h bar. Sorry, the Hamiltonian operator. That's the Schrodinger equation. And to say that this is the time translation operator is just saying that the Schrodinger equation is obeyed by the states. Okay, that's one point of quantum mechanics that I want to remind you. You know it already, of course. But the other point I want to remind you is that in quantum mechanics, operators do not necessarily commute with each other. So if I have an operator A and an operator B, they need not commute with each other. That is to say, A into B is not necessarily equal to B into A. There's a theorem I'm going to use that I will need, that e to the A plus B, these are operators A and B. Now, if they were not operators, if they were numbers, I would simply write that this is e to the A, e to the B. But actually, there's a commutator that comes in, and this is called the Baker-Campbell-Hausdorff theorem. It's not hard to derive, but this is something that I need to remind you as we move now into our derivation of the Feynman path integral. And let's now get into that. So what we want is the amplitude to go from A to B, and the Hamiltonian is what takes us there. There's TB minus TA because this particle was at point XA at time TA, and now it has to go to now it has to go to point B at time TB. As I said, we're just going to do single particle quantum mechanics. And here's the kinetic energy. Now, the kinetic energy is p squared over 2m, but we're going to deal with so many formulas that it's better to put m equal to 1. There's no loss of generality in that. Through dimensional analysis, you can put back m whenever you want to. Okay, so that's the kinetic energy plus the potential energy, and I remind you that in quantum mechanics, x and p are both operators, and the commutator of x with p is IH bar. Okay, now we're going to do this. We're going to calculate this amplitude in a number of steps. And since I don't want to write TA all the time, I'm just going to say TA is 0, TB is T, and I'm going to slice the time interval between 0 and T into n pieces. So each of those pieces is going to be of size epsilon. Epsilon is equal to T divided by n. And at the end of the game, I'm going to take n to infinity. But meanwhile, we'll just take a few of them. So here is time increasing from left to right, initial point, final point, and I am going to write e to the minus ht as a product of n exponentials. That's okay because h commutes with itself, so I can just add them together. I can write them in separate exponentials, no problem on that. Okay, now each of the h's is kinetic energy plus potential energy. And let's go to the next step. So here in this, I have eight intervals. So I'm now going to do a little trick. At each one of these points, here, 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 and here, that is to say at 7 points, 1 less than n, I'm going to insert the unit operator. Now, there's never anything wrong whenever you multiply by 1. You always get the same thing. So I am at liberty to use whatever unit operator I want. If I like this kind of unit operator or that kind of unit operator, it's my life. Okay, so I'm going to write the unit operator this way, xi, xi. And here I'm going to write a different unit operator where I'm integrating over the quantities dx I plus 1. Okay, and I do this at 7 points out of 8 because those are where the particle will be allowed to jump around. So the particle has to go from here to here, but it can be anywhere on the vertical axis. So in other words, I've got to integrate over all x1s here. Okay? Now, what does this mean? So I have 7 integrals, dx1 up till dx7, and I start from here. So I go from A to the next space interval, to the next, to the next, to the next, and I have to integrate over x1s, x2s, all the way up till xn minus 1. So that gives me an expression for the amplitude to go from A to B. And, you see, what this is just a product of amplitudes. So A to 1, 1 to 2, 2 to 3, etc. And then the last one, here it's the 8th one, here's the 7th one, A7 to 8. I have now these, I have the amplitude from A to B as a product of these amplitudes. And now my next job is to calculate each one of these amplitudes. A1 to 2, A2 to 3, etc. And so our next task will be to calculate this. Right? So here it is, that same thing. Now here I have used something. I've used the Baker-Campbell-Hausdorff theorem, which you saw. So you see, I can't really do this because there is also an e to the commutator term, right? You remember e to the exponential of a plus b is exponential of a times exponential of b times exponential of the commutator. But you see, exponential of the commutator we can throw away because a is of order epsilon, b is of order epsilon, a commutator of b is of order epsilon squared, and we are throwing away epsilon squared. And so this is completely correct as it stands, 2 order epsilon. Okay, now we will slowly make progress on this. This potential is a function of the position operator. The position operator acts on the ket and gives back the ket with the eigenvalue xi. So in fact, this is very simply done. It's just the same thing as above, but with x replaced by xi. Can't be simpler than that. Now I'll do more tricks. As I said, it is my privilege, my right to multiply by 1 and 1 in whatever form I like. So I'll put 1 as in this form with the momentum bras and kets. Okay, so that goes in here, and that takes us to the next step. So let's see what's happened. This stuff is as before over here. This is, remember that this over here is now just a number. By my putting in P here, I had to take the overlap, the scalar product with xi, and similarly, this over here with xi plus 1. Now, this exponential over here, you see that there was a operator squared, but that operator squared, when it acted on this, gave us the number. So this operator, p squared, became the number or the eigenvalue, p squared. And so what we have is something from which all the operators have disappeared. You can't see a hat over here on this, in this expression over here. Okay, now we need to remember that this is the momentum eigenfunction. The eigenfunctions are e to the I px. Of course, different normalizations, but if you're using this as the momentum unit operator, then you have to put 1 over square root of 2 pi h bar. And so we get this normalization here and this normalization here. And then it's just a matter of algebra. This e to the minus I Vx, I'll just pull it out over here because that doesn't depend on p. And then we have 2 pi h bar, which this and that. And you can see that I've just rewritten this over here and rewritten this into that over here. Okay, so I have to now do an integral over p of an exponential which has got an imaginary part. And now I mean, the exponent is imaginary. And we all know how to do Gaussian integrals. Well, here's the answer. And I suppose everybody over here must have seen this. Of course, there's always the thing that worries. This is an oscillating function, e to the minus I, and this is oscillating. It's not damped like in real Gaussian integrals. So how do you handle this? And the answer is you make an analytic continuation, or you slightly deform the path of integration. Unfortunately, we don't have time to do that, but just look up any book if this is mysterious. Next, it's pretty obvious that here one must complete the squares. So I've completed the squares, and in order to do that, I had to pull this thing out. Algebraically, I mean, this is an equality over here. All I've done is I've completed the square over there, and that's it. Okay. So this is now getting interesting, because in the limit where n goes to infinity, epsilon is getting smaller and smaller because we're making the time intervals smaller and smaller. Okay, once you do that, then as we learned in high school or maybe in kindergarten, that this becomes the speed. How much distance you cover in a small time interval epsilon. And so in the limit where you make a lot of these divisions, n goes to infinity, you get e to the I epsilon over h bar, x dot squared over 2 minus v of x. By the way, if I had not put m equal to 1, there would have been an m over here. And so this would have been half m x dot squared, which is the kinetic energy. So this over here is the kinetic energy minus the potential energy, which everyone knows is the Lagrangian. And there's this integration. This is obviously this thing. I put s equal to p minus this. Hence, our result that to go from the ith to the ith plus 1 position, the amplitude for that is equal to this. And now we're just going to multiply these amplitudes together. A to 1, 1 to 2, 2 to 3, etc., until we reach the final position. Okay, so we are almost at the point where we have derived the Feynman path integral. So it's just a product of amplitudes. And you see that each one of those amplitudes, so there were n such amplitudes, each one of them got us a square root. And so I have this 2 pi I h bar epsilon to the nth power, square root of the nth power, n over 2. And now is just a product of these. we're done actually, because we have now derived the Feynman path integral. So it's a to b is integral dx e to the IH s, where what is this dx? This is the limit as n goes to infinity. So you see what I've done over here, this epsilon is equal to t over n. So t over n, and remember there were n amplitudes. So that's why we have n over here, but there are only n minus 1 integrations. You remember I'd taken n equal to 8, but there were 7 integrals to be done. So there are 7 of these. I mean, infinity minus 1 of these. And this over here, this stuff is called the measure. And we've derived the measure over here. And we've derived S as being the integral of the Lagrangian. Why? Because this epsilon is really dt. And so this is dt into L, and I keep adding those n contributions, and that's exactly what an integral means. So I mean, you could put e to the you could put this factor I over h bar epsilon L, add them up as arguments of the same integral, as arguments of the same exponential. So we are finished. We're done. Now the only remaining thing to convince you that we've done something of some importance is that we'll compute simple cases of this, of the path integral. I should tell you that what we have over here is something very badly behaved. You see, you have n to the power n over 2, and in the limit that n goes to infinity, you obviously have infinity. So the measure, or the thing which multiplies dx1, dx2 up till dxn, that thing is infinite. And it gets people very upset when they hear that the measure is infinite. The normalization constant is infinite. But really, one should not be too worried, because it doesn't matter what the value of the normalization constant is. Even if we can calculate it, and usually we can't, it doesn't matter, because when you take expectation values of any physical quantity, they always cancel out. Okay, so now let's come back over here. In the simple cases, we have only Gaussian integrals to do. And the Gaussian integral is this e to the x squared, which we discussed before, is this. For the free particle, this S is just equal to this. For the free particle, V is equal to 0. And S is really this thing over here. You can, for the free particle, calculate n, and that's this. Here it is very nice and finite. But in the complicated things that we are going to do, this n will be infinite, or could be infinite. How would you do this? By the way, how would you calculate this? It's quite simple. You just when you take the integral dx1, dx2 up till dxn, and you have the exponential of epsilon times the Lagrangian, you just do integration in the normal way by completing squares, and that's how you get this answer. It's not so easy for this one, for the simple harmonic oscillator. But in principle, you could also do it that way. However, there are cleverer ways for doing it. And when we come to the second lecture of this course, I will show you how to actually do this calculation. One thing you may note, suppose that omega goes to 0 over here. So then the simple harmonic oscillator becomes a free particle if omega is 0, okay? So let's have omega approach 0. When omega approaches 0, what happens to this? Sine omega times this. So there's omega over there and omega TB minus TA at the bottom. The omega cancels out, and this factor becomes just this factor, I over 2h bar. What happens over here? Well, omega goes to 0, so this is xb minus xa squared, which is this. And so this and this become the same. So the simple harmonic oscillator and the free particle are the same in the limit that omega is 0. By the way, this amplitude that we've calculated to go from A to B, this is in quantum mechanics and quantum field theory also called the Green's function. And the Green's function has got two-particle Green's function in this case, has got all the information that you can possibly need about the system, which is quite amazing because you'll say, all I know is the amplitude to go from A to B. I would surely need to know more things like the wave function of the simple harmonic oscillator, what are its energies. Remember that a simple harmonic oscillator has an infinite number of excited states, and those are very complicated excited states. The higher ones are extremely complicated. The energies, of course, are n plus a half h bar omega. But how is that information present over here? It's amazingly, it's there. And you'll have to believe me because until next time, I won't be able to show you. So that's all for today. Next time, we will do what we will use the result of what we achieved today and go into imaginary time. And imaginary time is going to give us great rewards. And imaginary time is what will bring us closer to the subject of instantons, which is actually what we are here to talk about. Okay, so now if we have questions, we can have them.
So I was thinking that why you have taken the product of amplitude instead of the sum of the amplitude. Why the product? I was expecting that you are going to take the sum of the amplitudes.
Suppose I have to go from point A to point B. So first I have to go from A to x1, then from x1 to x2, then from x2 to x3, etc. I can't miss out any of them. So it has to be a product of them. And so in going from A to B, I can't miss out an intermediate step. Therefore, it's a product.
Sir, from very initial slide, you mentioned that quantum mechanics has infinite vacua. Can you explain that?
We're going to come to that later, but okay, since you've asked me the question, imagine that you look at a lattice of atoms, and the lattice is infinitely big. Then an electron, when it gets close to an atom, will want to be in one valley, but then there's not one valley, there are an infinite number of valleys. And so by a vacuum, I mean a place where the potential has a minimum. And there are an infinite number of minima in an infinite system. But of course, in quantum field theory, it's going to be even more interesting because we're going to have things called topological vacua.
All right.
This may be rather elementary question, but on your last slide, the literal variable for the amplitude goes from like script A to a regular A. So I just wanted to ask if there was like a change in the physical meaning of the amplitude, or it was just a choice of variable that you picked.
I don't know what you're referring to, so let's go to that. I need to know. By the way, you are welcome to have copies of the PDFs of these slides so that you can reflect on them for the next time, make up for things that you have not fully studied. Okay, now tell me exactly.
It's on the very last slide.
This is the last.
Yeah, on the top, like you've written A, like the amplitude A with a script, whereas in like the lower, like for the answers for a free particle and simple harmonic oscillator, the A changes. So is that just like your choice of how you wrote A, or is it like a physical change?
No, I'm not getting one. You want to come here and which A?
Like literally just the variable of the amplitude.
Yeah.
It's just changing like literal A.
Oh, okay. So in doing the tech,
Okay.
I use MathCal over there, and here.
I was just making sure there was no change.
Okay, yeah. No, but you have a real eye for scripts.
It's been quite an issue in physics classes where a professor just uses a different variable.
No. Yeah, I mean exactly the same thing. I'll go home and change the script. Okay.
Sir, when omega approaches to 0, then what happened to the last term, that is minus 2xaxb?
You see, when omega is 0, then this is cosine of 0 is 1, right? So this is xb squared plus xa squared minus 2xaxb, which is xb minus xa squared.
Okay.
So that's exactly the same as over here. Okay. So if there are no more questions, then we will meet next week. And next week, then we will first encounter instantons. This was the lead up towards that. We needed the path integral technique in order to even begin talking about instantons.